¿Qué tal? Bienvenidos a todos ustedes. Es un placer tener esta audiencia tan grande. Bienvenidos a la sesión del Coloquio Interinstitucional de Análisis y sus Aplicaciones. Entonces, por favor, si nos puede hacer el favor el doctor Héctor Benítez, director del IIMAS, nos puede dar unas palabras.
Gracias, Miguel. Gracias. Buenos días a todos. Muchas gracias, Miguel, por la introducción. Creo yo, y lo he platicado con todos los colegas, que lo más importante es generar espacios para desarrollar las ideas, para trabajarlas, para convivir, para comunicarnos, sencillamente, y para, al final de cuentas, tener un buen momento, pasar un buen momento entre colegas y sobre todo discutiendo cosas interesantes, cosas de alto nivel. Pero que nos llenen y que nos hagan sabrosa la mañana, sabrosa la tarde, no sé. En fin, pero que sea un trabajo de mucha valía para todos nosotros. La idea del coloquio interinstitucional tiene ya varios años, muchos de ustedes han participado ya en él, al menos un par de años, creo. Y es algo, a mí cuando me lo presentaron, Miguel Ballesteros, el doctor Ballesteros me lo platicó en su momento, se me hizo una muy buena idea, que era hacer algo entre las distintas entidades que desarrollan o que estudian la matemática y que darle sentido como un sentido unamita, más allá de un sentido de una u otra entidad, sino un sentido unamita. Y en ese sentido se generó este espacio transversal entre los dos institutos y la Facultad de Ciencias, su facultad. Entonces, en este grupo de entidades, pues se buscó generar el espacio que nos permitiera platicar, estudiar y trabajar y cultivar el área de análisis matemáticos. Siendo ya el segundo año que se tiene este coloquio interinstitucional y que ha tenido muy buen éxito, y muestra de ello pues es esto, que no tenemos lugares ahorita disponibles para todos ustedes, para que estén todos cómodamente sentados. Eso está mal, no está bien que haya gente parada, pero por otro lado, qué bueno, ¿no? Qué bueno que no esté la mitad del auditorio vacío, o que nada más estén los colegas que van a exponer y los colegas que los hayan invitado, ¿no? Eso sería muy feo que ha pasado, pero no queremos que pase eso. Entonces, esto nos lleva también al gusto por el área y el gusto por, sobre todo eso, creo que es la palabra correcta, el gusto por el área y el gusto por cultivarla. Tengo más que decir que disfruten este coloquio, disfruten el Congreso de la Sociedad Matemática Mexicana, el que se está desarrollando este año aquí en la UNAM. No es común que venga a Ciudad de México el Congreso, por muchas razones, la propia sociedad, y está bien, se busca que se mueva alrededor del país, y este año lo tenemos aquí en la Ciudad de México, entonces habrá que disfrutarlo, habrá que ser parte de él, asistir a sus distintas foros, reuniones, conferencias que se van a realizar o que se han venido realizando toda esta semana. Y una de ellas es esta. Como les decía, disfrútenlo primero, sáquenle provecho. Y segundo, colaboren. Y colaborar es de muchas formas. Y colaborar es platicar, contribuir, hablar, preguntar, cuestionar, dar una retroalimentación de las propias ideas que uno tiene. Creo que eso es lo más importante y lo que enriquece a cualquier área de conocimiento, ese diálogo constructivo y profundo. Pues sin más, y felicitando a los organizadores de este evento, a los organizadores académicos de este evento, no tengo más que decir, más que tengan un muy buen inicio de coloquio, tengan una muy buena mañana con todos ahí, con los expositores de muy alto nivel que aceptaron venir. Thank you for being here at IIMAS and especially at UNAM. Y sin más nada, pues muchas felicidades, muchas gracias y pues bienvenidos sean todos a este coloquio. Gracias. Ahora, Miguel.
Enseguida, Ricardo Beder va a presentar al ponente.
Well, thank you, and I guess we switch to English because now somehow the mathematics begins. And thank you all of you for coming. Please come in, Rudy. I will try to be brief, but let me say a few words about Professor Rudi Weikard, who is the first speaker. He obtained his PhD in 1987 in the Technical University of Braunschweig. His advisor was Heinz Siedentop. And since 1990, he is with the University of Alabama at Birmingham. He's one of the leading experts in mathematical physics in many areas, in particular where inverse problems and inverse resonance problems, where he's one of the researchers that has made many important contributions. He also works in differential equations in the complex domain, in abelian integrals. And besides his distinguished career as a mathematician and a researcher, he distinguished himself in the organization of meetings. In particular, were a series, the University of Alabama at Birmingham Differential Equation and Mathematical Physics, that play an essential role during so many years, and for quite a few generations, including my own. It was a focal point. Each 2 or 3 years we will meet there from all over the world. We will have exchanges and meet people and learn many things. And this was a very important series of conference. And I guess many of us are looking eventually to the next one, right, of this series. And then the right is inverse resonance problems. So Rudy, please.
Okay. Does this work? The mic? Okay. Well, let me begin by thanking the Institute and Ricardo Veda for the invitation to this event. It's a great pleasure for me to be in Mexico, or Mexico, the way you say it. It's my first time, so I'm very thrilled. This is the only Spanish which will appear, unfortunately. Okay, the title of my talk is on the inverse resonance problem. And I will begin with giving the dues to my collaborators. So I have worked on various things which I will present today with Christa Benewitz in Lund in Sweden, my student Matthew Bledsoe, Malcolm Brown at the University of Cardiff in Great Britain, my colleague Ian Knowles, he is another colleague of mine, Roman Sterenberg, and in addition Marco Marletta, also at Cardiff, and Sergei Naboko in St. Petersburg. Okay, we begin with the introduction history. Many people will begin an introduction to this topic with a paper by the Soviet, let me say, astrophysicist maybe, Ambarzumian, and he wrote in 19. I don't know how to do this. So in 1928, he wrote a paper. He wrote it in German. I have translated this part here, and it reads, if indeed the spectrum of eigenvalues define the differential equation completely, then it would be possible, for instance, to determine practically the structure of a system of atoms from the spectrum, i.e. to solve the problem which is, so to speak, reciprocal to Schrödinger's problem. So Schrödinger's problem, the Schrödinger equation, was if you know what the system is, you might want to determine what the spectrum of the system is. But here, this is the inverse version of that. So if you know if you have information about the spectrum, then you want to get, in the inverse way, you want to get information about the structure of the system. So this is sort of the birth of inverse spectral theory in 1928. Okay. And now let me begin with sort of the main equation in this business. So this is the famous Schrödinger equation. The function Q here is called the potential. It describes the physics of the system. The second derivative here comes, thinking physically, comes from the kinetic energy of the system. Q, as I said, is the potential energy. Lambda here is the spectral parameter. It's a complex number in general. And one poses this differential equation on an interval 0b, where b could be finite or infinite, or maybe sometimes one poses it on the full line, so from minus infinity to infinity. All these are possible. Okay, one may have to also put boundary conditions. One has to put the boundary condition at 0, this point. And sometimes one may have to put the boundary condition at the right-hand endpoint. And sometimes maybe not, so it depends a little bit on Q, in fact. Okay, and here I've listed some boundary conditions. This one, when you ask that the function you are looking for here, that it will vanish at the initial point, you call this a Dirichlet boundary condition. If you ask that the derivative vanish at the initial point, you call this a Neumann condition. And they are both special cases of the Robin condition, which is this one. So where you have sort of a mixture of the two cases. And in the case alpha equals 0, you get one of them. And in the case alpha equals pi over 2, you get the other one of the previous ones. Okay, we will mostly, unless otherwise mentioned, I will, if I forget to say what Dirichlet what condition I have in mind, then I will have the Dirichlet condition in mind in the future. Okay, so here is what Ambar-Zumian actually found out in his paper in 1928. So he looked at the very special case, namely he had a finite interval, so B is now finite, and the potential is a continuous function. And in this case, if you put the Neumann, this is a situation where you have to put the boundary condition at either end. So if you put the Neumann condition at 0 and the Neumann condition at B, and if you then find out what the eigenvalues are, and they are exactly the ones which you would have if your potential was the 0 potential, so if Q was the 0 function, if those eigenvalues would be exactly those, then you would know that the potential actually was 0. So it's a uniqueness problem. There could be no other potential which would produce these eigenvalues. This was Ambar-Zumian's result in 1928. And took almost 20 years to make some progress on this program. Borg in 1946. He showed that in general, so if you do not only compare with the 0 potential, then knowing just one set of eigenvalues like here is not going to be enough to obtain a uniqueness theorem. Instead, you need two sets of eigenvalues. So maybe you fix on the left-hand side, you fix a Dirichlet condition, and on the right-hand side, you put a Neumann condition. You obtain the eigenvalues, and then you change the condition on the right-hand side, and you put another Dirichlet condition or one of these Robin conditions or something, and you get another set of eigenvalues. If you have both of these sets of eigenvalues, then they could come only from one potential. So there would be only one potential which could produce those two sets of eigenvalues. So this was Borg's result in 1946. As you see, it's almost 20 years after Ambar-Zumian. And then there were more results very rapidly in the late 40s and 50s. Levinson showed that you could obtain the uniqueness theorem by having one set of eigenvalues. And if you knew the Neumann data, so if you have the Dirichlet eigenfunctions, so these are the functions which vanish at both endpoints, say, and then you had and if you then had the Neumann data of these eigenfunctions, Neumann data means you now know what the what the derivative, so the values of the eigenfunctions are 0 at both endpoints if you put directly. And if you now know what the derivatives are, they cannot also be 0. But if you know what their values are, then this replaces the second spectrum. So you can get it from one spectrum, but you need not only the eigenvalues, you need additional information. So this was Levinson's, and Marchenko was a similar result. In his case, he didn't use the Neumann data of the eigenfunctions, but the norming constants. So if you have the eigenfunction and you know what norm it has, then you could also recover, or you would have a uniqueness theorem for the potential. Okay. So this was, all these things happened on a finite interval, and now people were interested in generalizing this. And we now allow for B to be infinity. Maybe Q doesn't have to be continuous as Ambar-Zumian was assuming. So locally integrable will do. And there are now special solutions for the differential equation. They are called the Weil-Titchmarsh solutions. And the solution C here is the solution of the Schrödinger equation, which has specified initial conditions. C of 0 is equal to 1, and its derivative is equal to 0. And the function S here is another solution where the initial conditions are just the reverse. So the function is 0, and the derivative is 1. Of course, solutions to the initial value problems are uniquely determined. So these C and S, they are uniquely determined. And if you now have either the right boundary condition, maybe you don't need a boundary condition. So you would ask, or you would always know that a solution exists which is square integrable. And if there's only up to multiples, only one such solution, then you choose this coefficient here so that this is the solution which is square integrable. And if you need a boundary condition at infinity, then you would put that boundary condition and you would ask M to be that coefficient such that this function satisfies the boundary condition on the right, but you do not care what happens on the left. So these are, and that makes this M here, for every lambda, at least for every non-real lambda, this M here is uniquely defined by that. And this M is the Weil-Titchmarsh function. So these are the Weil-Titchmarsh solutions, and M is the Weil-Titchmarsh function. Okay? And they have the Herglotz-Nevanlina property. So that is very important. This is a piece of complex analysis. And the Herglotz-Nevanlina property says that the function M is analytic in both the upper and the lower half plane. It may not be analytic along the real axis, but in both the upper and the lower half plane it is analytic. And in the upper half plane, the imaginary part of the function is positive, and in the lower half plane, the imaginary part of the function is negative. And such functions are called Herglotz-Nevanlina functions. And they have this interesting property. So every Herglotz-Nevanlina function can be written in this form. There's a constant A, a positive constant A real constant B, and a positive measure rho, such that the function is given by this integral representation. And conversely, every such thing here is going to be a Herglotz-Nevanlina function. So this... And now what we are after here is this function rho, or measure rho. It is called the spectral measure. It is uniquely determined by M, and of course it also determines M uniquely. So these are two different things which contain the same information. This is the spectral measure. And what is now the important thing about this Weil-Titchmarsh function? It determines the eigenvalues and the continuous spectrum. Namely, there are those points where the function M ceases to be analytic. Remember, the function M is analytic in both the upper and the lower half plane. It could be analytic at certain parts of the real line also, but it must not be, it may not be. And those points where it's not analytic, if it's an isolated point, that would be an eigenvalue. And if it's an interval or something, then you would have continuous spectrum at that places. So M determines the spectrum of the situation. Okay, and now comes the Gelfand-Levitan theorem, which generalizes all the ones we had before, and it says the spectral function, this function rho, determines the potential uniquely. Okay, now we come, this was the inverse spectral theory. Now we come to inverse scattering theory. I shouldn't say anything about this here because Ricardo, he's much more knowledgeable about these things, so I'm liable to make a fool of myself here. All right, so scattering is a perturbative process. That means one compares solutions of two different potentials. One thinks of knowing this one very well, we will deal with Q not equal 0, which we know very well. We know what the solutions are. In this case, we learn in our first differential equations course how to solve the equation in this situation and so forth. And one tries to compare Q and Q naught. So they should be close in some sense. Okay, and when you look at the Q naught equals 0, then you know that the solutions are these. Remember, the equation is then minus the second derivative equals lambda times y. Lambda we write as k squared, and then the solutions are, of course, exponential functions. And in order to make it, I mean, you could choose k in two ways here, of course. We choose so that the imaginary part of k is non-negative. Okay, and we need a scattering condition in order to make this comparison. So this is what it means. These are sufficiently close. Namely, the function q should be integrable, and its first moment should also be integrable. This is called the scattering condition. And this scattering condition guarantees finitely many eigenvalues. They're all negative, and it guarantees essential spectrum, continuous spectrum from 0 to infinity. Okay. And then we have the Jost solutions. So these are now the solutions for the potential Q, rather. These are the solutions for Q naught, and these ones are the solutions for Q, and they are now closely related to the original ones here. So the Jost solutions are given by this integral representation. We have this integral kernel K here. It's going to play a large role later on if I get there. Is there a clock in this room? Okay. So, and here we have some interesting properties about the Jost solution. If you fix x and treat it as a function of k, then it is an analytic function in both in the upper half plane. We only consider the upper half plane of k, and it is continuous in the closed upper half plane. But not, it may not be analytic on the real line, but it is continuous on the real line, up to the real line. And then we have the Jost function. It is if you evaluate the Jost solution at x equals 0 at our left-hand endpoint, and you treat it as a function of k, this square root of lambda. This is called the Jost function. And we'll come back to that, I guess. Then there's Marchenko's inverse scattering theorems from 1955, and it says the eigenvalues, and then the norming, these are the norms of the eigenfunctions, and the scattering phase, which is obtained from the Jost function by this expression here. So delta is the scattering phase. So the Jost function tells you what the scattering phase is. These information, they determine the potential uniquely. Okay, now we come to resonances. So if Q's decays super exponentially, so you can do inverse spectral theory. You don't have to have any condition on Q except that it be locally integrable. To do scattering theory, you have to ask that it satisfy the scattering condition, that it be integrable and the first moment be integrable. But now we ask even more of the potential Q, namely that it decays very fast at infinity. So if it decays super exponentially, then, and for fixed x, then this Jost solution as a function of k can be analytically continued to the lower half of the k-plane. It was already analytic in the upper half plane and continues up to the real line, but now it turns out it actually extends analytically to the full k-plane. And one could say a similar thing about the m function, which is not the function of k, but the function of lambda, and then one has to get in the notion of the Riemann surface. And one cuts open the plane along the spectrum, and there is another second sheet behind that, but I don't want to go into this. Okay, so now we define the resonances. First, what would be the eigenvalues? Well, if the Jost function it is asymptotically behaves like e to the ikx, I didn't make this clear enough earlier. Asymptotically, the Jost function behaves like the unperturbed one, and that makes it square integrable when k is in the upper half plane. And when you now ask that at 0 it is equal to 0, then it also satisfies the boundary conditions on the left, and therefore it is an eigenfunction, and the k squared, remember lambda is equal to k squared, is then an eigenvalue of the problem. And psi, as I said, is the eigenfunction. So these are the eigenvalues. The k's, the eigenvalues are of course real, so k squared is real. That means in terms of k, the eigenvalues lie along the positive imaginary axis. And now our function is also analytic in the lower half plane, and we could have zeros of the Jost function in the lower half plane. And if that's the case, this function will not be square integrable, but it will satisfy the boundary condition on the left, and in this case we call k square a resonance. Okay, and the idea behind all of this, what Ambar-Zumyan had in mind, that you can see the eigenvalues and also the resonances, you can see them in spectroscopy. You might think of the Balmer series for the hydrogen atom. All these things are very much related to these. Okay. So now here's the inverse resonance theorem. So suppose that Q is compactly supported. That certainly, excuse me, that certainly makes it super exponentially decaying. And then if this is the case, then if you know the location of all the eigenvalues and the resonances, then Q is uniquely determined. So here in this case, we will not have the need to know any of the norming constants or any of this thing. For the resonances, there wouldn't be any norming constants anyway, because that would be infinity. So just the location of all the eigenvalues and the resonances, they determine Q uniquely. Okay, here's a short proof of this. It relies on certain things, of course. So first of all, in this case, the Jost function is everywhere analytic, so it's an entire function. It has growth order 1. As a function of k, it has growth order 1, and there is a famous theorem by Hadamard which tells you if you know all its zeros, then you know the function to a certain extent. So let's see what Hadamard's theorem says. So if you know an entire function of growth order 1, and you know if you know all the zeros of an entire function of growth order 1 and their multiplicities, then you know the function up to a factor e to the ak plus b. This is due to the growth order being 1. So, and now, because we know that regardless what Q is, the behavior of the Jost function along the positive imaginary axis, the asymptotic behavior is equal to 1. So that allows you to determine what, if you change A or B from what they should be, then you will not get this behavior anymore. So this here will determine what A and B is, and then we know all the zeros. So what we have now obtained from those zeros is we know what this function psi is as a function of k. And then Marchenko's inverse scattering theorem says, okay, then we have everything, because we know the location of the eigenvalues. Those are the roots of psi in the upper half plane. Square them. We know the norming constants. They can be computed from the Yost functions by this. The dot here means the derivative with respect to k. And the scattering phase I was mentioning earlier is this one. So the function psi determines all this thing, and then Marchenko's inverse scattering theorem tells you you know everything. All right, this seemed to go unnoticed somehow. Maybe people weren't too interested in the resonances at the time. It went unnoticed for 40 years. Korotyaev wrote a paper in 2000 about this. Then Swirsky said, well, I had made this, I've seen this earlier in 1988, but he didn't want to publish it at the time. So. Okay. Now I'll be looking at the asymptotic distribution of the resonances. So the uniqueness theorem requires the knowledge of all the eigenvalues and the resonances. If you know them all, then you have a unique Q, and if you don't know them all, then you have freedom to make choices. So, and now we look at the particular case. Suppose the potential is supported on this compact interval. It is absolutely continuous there. And if it has a jump discontinuity at R, so beyond its 0, and actually does jump down to zero, then you can find out how the resonances are asymptotically. This is a line in the complex, in the lower half of the complex plane, and the resonances will be near that line eventually. So what it tells you is, if you change R by a micron, or if you change the size of Q by an electron volt or something, then this line will be different eventually. And that means the asymptotics of these resonances will be different. And that means, so if you think like a physicist, changing the potential on the last micron or so, that shouldn't make any difference. You wouldn't see that in a laboratory. So the physical quantities, they should not be encoded in these large resonances, which now would have to change all of them. Okay, so this is the case. They produce different asymptotics. This leads us to the claim, or that large resonances are physically insignificant. So they're not too important when you try to recover something. So, and we want to state and prove this mathematically. There's a similar issue when you have a compact interval. In this case, there are no resonances. There are only eigenvalues. There's no continuous spectrum. There are only eigenvalues. And the inverse theorem is that if you know all these eigenvalues and maybe the norming constants, things like that, then you find out what the potential is. But in practice, it is impossible to know all the eigenvalues. There's a similar thing in computed tomography. The theorem says, by Radon in 1917, that if you know the attenuation coefficient along any ray through a body, then you can find out what is the cause of the attenuation, and you find out where are the bones and where are the other pieces of. But in a computed tomography, you cannot take infinitely many of these pictures. So you can only take finitely many. And the question is, what does finite data, what is it able to tell you? So this question was first posed by Hochstadt in 1973. And, okay, yes. And then Rondell and Sachs, they had remarkable examples, and this was in 1992, and reasons why one could hope for a reasonable recovery. But it wasn't a theorem in that sense. Then other people, so they had some kind of algorithm by which they did this, and other people here, there's an example of something. They had other algorithms and still more approaches, and you could ask yourself, okay, all these people have their algorithms, and in the end they start from finite data. Everybody computes something. which one is the right one, or how far away are these answers from each other and from the truth? This is the question. Okay. So, and here are some of the results. All right, so this is sort of the culmination maybe of my work on this topic. This is work I did together with Marco Marletta and Roman Sternberg. And this is the theorem here. And if I have time, in the end I will say a little bit about how to prove this, like some idea. It's very technical actually. So we have two potentials, Q and Q tilde, and they are supported in the interval 0, 1, and we ask that their 1 norms are bounded by some given constant. We also ask that the P norm of their difference is bounded by some known constant. P is a number in the interval larger than 1. Less than or equal to 2 is not so important. So P is a number larger than 1. And now imagine a disk, a large disk of radius r, and inside of that disk all the resonances and all the eigenvalues associated with Q, and those associated with Q naught, they coincide. Or maybe they only almost coincide, they are epsilon close to each other. But to make it easy, imagine they coincide. And outside that large disk, remember, large resonances, nobody cares. Outside this large disk, we don't ask anything of these resonances. So only inside the disk of radius r, we ask that the resonances and eigenvalues of Q coincide with those for Q tilde. So if we have this situation, then we get the following result. It's a very weak norm here which we have. So you have for every x, I'm saying this here, okay, it's in the supremum. So for every x, the absolute value of this integral, the difference of these potentials, is going to be controlled by this function here. And this function tends to 0 as r tends to infinity. So yes, if you know all the resonances, then there is uniqueness, right? But you have to also ask that as r goes to infinity, r to the 1/6 also goes to infinity. In this case, you have to let epsilon go to 0 a little bit faster, so this thing goes to 0. So if epsilon was equal to 0, then this would be equal to 0 and you wouldn't have a problem. So in particular, we would recover the uniqueness theorem from this one. Because if epsilon is equal to 0, and if this then goes to 0, for all x means that this difference has to be 0 almost everywhere. Okay, so this is the stability theorem. So if resonances are close, then the potentials themselves, they can behave only this badly, no worse. Okay, and we have other results historically. They not there right now. So first of all, 1983, Ria Bushko, he looked at, so remember there were two sets of eigenvalues. One are called lambdas and the others are called mu, and they are sequences, of course. And you take the little L2 norms, and then he showed that if these little L2 norms are bounded by something, then the big L2 norm of the difference, maybe this should be Q tilde here. Q and Q tilde, they would be the same. Or they would be this, they would be bounded by this. There's a result by Joyce McLaughlin, where instead of two spectra, one has one spectrum and the norming constants. And then I had a result with Marco Marletta. So this was in 2005. This was our first result in this area. And so in this case, we only have eigenvalues. So we ask now that that the first n eigenvalues of the Dirichlet problem and the Dirichlet-Neumann problem, that they are all maybe coincide of these two, or that they are epsilon close, whichever you want. So if they coincide, let's say, then epsilon is equal to 0. Then again, for all x, this the absolute value of this integral is bounded by this function, and the function goes to 0, but you have to make sure that epsilon log n goes to 0 also. So if n goes to infinity, the number of eigenvalues you ask to be the same for the two potentials, then epsilon has to go to 0. If you knew the locations exactly and epsilon would be 0, then of course this is not a problem here. So this is a situation for a compact interval. And one can now look at what these large eigenvalues, what they are responsible for. Suppose you have two potentials, one is 0 and one is sine kx. K is now just a large number. It's not the same k as before, a large real number. And the idea is if you measure voltage over, you have to measure it over some even small interval, perhaps. So if you measure it from here to here, you don't know whether you have, whether you put your sensor on this point or this point. Maybe a little bit different if you think like a physicist, and therefore you don't know exactly. If you have a potential which is 0 or potential which varies very much, then the average would be 0 over this, even over a short interval, and therefore the physicist would not be able to detect this. If you have a 0 potential, or if you have a potential which is oscillating very wildly on a short interval. So if k is very large, then you would expect that, and it happens, that the first few eigenvalues, that they are very similar. And indeed, so if k is equal to 100, then the first 16 eigenvalues are practically identical, and then it goes off, comes back again. If k is equal to 400, then the first 64 eigenvalues are practically identical. So we've drawn the differences of these eigenvalues here. And then it jumps up to here, and then it comes back again. So this is what happens there. So then there are discrete problems. There are discrete Schrödinger equations, and there are orthogonal polynomials which are related to Jacobi difference equations, and one can pose similar questions about these things, and we did pose them because we weren't able to answer the big question which I presented earlier, which I said was the culmination of our work. We didn't know how to do this initially, so we first did some easier things. So there's a discrete Schrödinger equation in 2005 with Malcolm Brown and Sergei Nabokov. We proved uniqueness, and with Marco Maletta we proved stability for the discrete Schrödinger equation. And then we looked with Brown and Nabokov something called the Hermit Operators. So the difference equation looks now like this, or the difference operator looks like this. B is sort of the potential. For Schrödinger, by the way, this coefficient is 1 and this coefficient is 1. So that's the difference. And then there are also orthogonal polynomials on the unit circle. There are orthogonal polynomials on the real line. These are the famous orthogonal polynomials like Hermit and Legendre and all Laguerre and all these things. But there are also orthogonal polynomials on the unit circle. And back in the 10, 15 years ago, they were very en vogue. And we proved uniqueness for these. CMV stands for Cantero, Moral, and Velázquez. These are 3 Spaniards who worked on this business. And so we proved uniqueness. And right, yes. Okay, and what we have? Okay, these are Jacobi operators. So again, these are related to orthogonal polynomials on the full line. And we were treating 3 particular cases. If the spectrum is a full real line, or the spectrum is a half line, or the spectrum is one finite interval. But you will notice there are no gaps in the spectrum. And there's a reason for that. And probably come back to that a little later. Okay, then there are full line problems. So far I've always been talking about you have a half-line problem. It starts at 0 and goes maybe to infinity, but you could have scattering on a full line. And my student Matthew Bledsoe treated that case, the discrete case and the continuous case. In this case, it turns out that the eigenvalues and resonances, which are the poles of the reflection coefficient. For those who know, if you know the reflection coefficient in this case, then you can determine, or the potential is uniquely determined, but the eigenvalues and resonances will now not determine the reflection coefficient. You also need the zeros of it in order to, so it's a little bit different. The zeros of the reflection coefficient are also needed. And then there's another thing I've done in the last few years. These are left definite operators. So if Q is a non-negative potential, so this looks almost like a Schrödinger equation. If W was equal to 1, then this would be the Schrödinger equation. But now sometimes one is interested in a situation of this differential equation where W is allowed to change sign. And if W is positive, then you use a weighted L2 space as your Hilbert space to do your spectral theory in. But if W changes sign, then this is not possible anymore. But if instead you have a positive Q, you can use the left-hand side to determine a product in a Hilbert space. And this is why these operators are called left definite operators. So here's the underlying Hilbert space. So it's all the functions which are absolutely continuous locally, and you ask that their derivative and square root of Q, remember Q is now positive, times the function that they are square integrable. So this turns out to be a Hilbert space. And then you can do a spectral and a scattering theory about these, and we've done that with Benowitz and Brown for the half-line case, 2009, for the full-line case in 2012. Okay. Okay, there's an inverse resonance problem for this thing too here. This is scattering and spectral theory. The inverse resonance problem was done, I did that with my student Matt, 2015. Okay, how much time do I have now, Ricardo? 20 minutes, okay. So I will now say a few words about how one could prove this theorem I had mentioned earlier, which I said was our major theorem. So it's actually very technical, so I can give you only an idea of how one would approach it and maybe what goes into this. Okay, so first there were the transformation operators. I think I mentioned them earlier. So if you have two potentials, you have two Jost functions. If, for instance, the the Q, if it was the zero potential, then this would be e to the izx. Here we would have e to the izt, and then we would have seen this formula previously. So if you compare two general potentials, then you have such a connection between the Jost functions. And this K here is, this is called the transformation operator. This is the kernel of the transformation operator, and it is satisfied by, it satisfies a wave equation. And here's the wave equation, which is satisfied by this potential, by this kernel. Here's the wave operator, and then here you have a right-hand side. And you have boundary conditions, of course, for this PDE. And here are the boundary conditions. You ask that K function the kernel itself, and then the x derivative, the kernel itself is 0, and the x derivative is equal to the t derivative. So I think x goes this way, t goes that way. So that's those are two boundary conditions, and then you have this here. The x derivative plus the t derivative is 1/2 times the difference of the potentials. So the difference of the potentials, you see, this is what we want to determine, or rather the integrals. And one sees here how that comes about, that one is able to get one's hands onto the difference of these potentials. So this is what we need to estimate. So kxx, if you integrate this here, if you differentiate kxx, then you get this. So therefore kxx, the kernel on the diagonal is the integral of this, and this is exactly the quantity which we will be able to integrate, to estimate. And that means we need to estimate the kernel on the diagonal. This is the diagonal. No, but our potentials are compactly supported. This is why this happens. Okay, here's our equation again. And now one can formulate this with different conditions. So suppose the function k is given on this line, and you know that it is 0 on this line. Yeah, this was a good question by Ricardo. So the world ends here at 1 because the support of the potential is on the interval 0, 1. So that was a good question. So you can determine the k here in this triangle also if you know what it is on this side, and if you know that it is equal to 0 on this side. Okay, and how this is done. You do this by iteration. You start with a k0, and it's, if you know it on the left-hand side of the triangle, if you know the function k there, then you have defined your k0, and now you iterate. So if you know what kn is, where's kn? Here is kn. If you know what kn is, then you can compute kn plus 1 by computing this double integral. So it's a bit nasty, maybe. And if you have computed all these kns and you sum them up, then you will get the kernel. So this is standard in this business of solving wave equations, and we just utilize this for our purposes. So in order to do this process, what we need to get started. We need to have this one, and all the others one are gotten by iteration. So we need to know what this is. So we need to know what k is for the first argument being equal to 0. That's the goal, what we have to try to do. And now we compare our two, so we have our two potentials. Here is the kernel of the transformation operator, which we want to find out. But we can also compare each of them with the potential 0, in which case we have kernels kq and kq tilde. These are comparing these guys with potential 0 instead of with each other. And then, of course, we have this commuting triangle here. Instead of going from here to here, we could go from here to here. So first with an inverse transformation operator, and then with this transformation operator. And if you do this, then you find the following equation. So the k0t, this is the thing we were interested in. It is given by the difference of these two kernels here. It appears here, and it appears inside of this integral. So this is what we need to know about. So this is what we need to estimate. The difference of these things. If we know about what that is, then we can get information about that, which is our goal. All right, now how do we get the difference of these kernels? Remember, what we know is something about the resonances, which are the zeros of the Yost solution. So we have to bring these Yost solutions into the game at some point. And here's the equation. For x equals 0, we have e to the I zx here, but for x equals 0, it's 1. So we get this expression. And we have a similar expression for the tilde version of this thing. And now we take the difference of these two, and then the difference of these kernels will appear in this integral. So you see that the difference of these kernels, if you Fourier transform it, you get the difference of the Yoast functions, or maybe you want to view it the other way. If you inverse Fourier transform the difference of the Yoast functions, you get this difference of these kernels, which is what we were after, according to the previous slide. So here's the inverse Fourier transform, so we need to estimate. We need to estimate the difference of these two Yoast functions. And then by doing this inverse Fourier transform, we would get information about the difference of these two kernels. And then, so once you have done all this, then you have to really go back and check all your inequalities, etc. So this only provides for the idea of why you try to do what you do. Okay. So how does it work? Why do we know anything about Yoast functions? This is because of Hadamard's factorization theorem. Very beautiful stuff in complex analysis. So if you have an entire function of growth order at most 1, then the function, I mentioned this earlier, didn't write it out, the z-ends are the zeros, repeated according to their multiplicities if need be. You have this extra factor here, which is because you may have growth order 1, you have to have this factor. So this product here is determined if you know what all these zeros are of the function. So if you put z equal to zn, then you get the 0 here in this product, and then the function has a 0. So these are exactly the zeros of the function. And if you know what all the zeros are, you know what this product is, and then you also know what this is. If z equals 0 is the 0 itself, is multiplicity and not, you have this factor. And you also have an a plus b times z, as I mentioned earlier. So this is Hadamard's factorization theorem. And now suppose that the first n zeros coincide between, you have two such functions, and the first n zeros coincide, and you don't care what happens afterwards. So in functions of growth order 1, the number of zeros in the disk of radius r is approximately 2e times the radius. So you have to know such things here, which you know from complex analysis. Now you take the quotient, and then these terms here, these factors, they all cancel out if the z-ends are the same for the first ones. And you have, this one will cancel out. You have maybe two different ABs, which is this one, and then you have these pi functions, which are just what remains after you have cancelled the first n of the zeros. Then you have that this stuff here remains. But the advantage now is that these z-ends are very big now. And z maybe is not so big, and therefore this is approximately equal to 1, and you can control what this product is. In fact, here we have it. If z is less than r, then the difference of this product here to 1 is controlled by this quantity. And if you have now that z is less than r to the 1/3, then you have 2/3 here, r to the 2/3 divided by r, you get something which goes to 0 as r goes to infinity. So these products will be practically equal to 1 for large r if z is not too big. Okay, I guess that's what I'm saying here. So this is how the knowledge of the zeros of these Yoast functions, these used to be called psi here, these things, how the knowledge of these Yoast functions helps us to determine something about the quotient. We were really after the difference of these two functions, but if you know something about the quotient, that's also very helpful. So maybe I should skip those details here, it's becoming very technical. So these are these elementary factors in Hadamard's or Weierstrass theory about factoring entire functions. And you need to know things about the asymptotic behavior. You need to know such inequalities. And that allows you to get this Okay, so let me go back a little bit because we now have some first result, but we have the requirement that z is less than r to the 1/3, but we need to know also something about the large z. And this is what the next slide is about. Okay, so we go back to this difference here, and we rewrite it now as this here, and the function h, which I have not spelled out what it is, it turns out to be absolutely continuous. If q and q tilde were itself continuous, then the kq and the kq tilde, they would be absolutely continuous, and it would be make no problem to take their derivatives and things like that. But in general, you have to work a little bit harder when these things are only locally integrable. So, but you take sort of the first term out, and then you are left with the rest here is something which it and its derivative is absolutely continuous. And one should also say one knows something about the size of these functions in terms of the variable t. So they are. Okay, now we integrate by parts. We get this function. I think we had it already earlier, this equation. If you integrate by parts here, then you get this here. This is the sort of the boundary term, and then you have g hat is just an abbreviation for this thing. And then you want to control how big this is. And that needs something called the Hausdorff-Young inequality. It tells you that so we think of G as being the Fourier transform of something. Yes. So the Hausdorff-Young inequality, and you might remember that we needed that Q minus Q tilde was bounded in some P norm. So the Hausdorff-Young inequality for such P says that the Q norm, Q being the associate coefficient to P, that the Q norm of the Fourier transform is bounded by this number times the P norm of the function G itself. So, and if you use these things in here, then you get some control in the situation when Z is larger than R to the 1/6. Okay, so I mentioned this, that Q minus Q tilde has to be in LP so that we can actually use the Hausdorff-Young inequality. And so this thing then allows here to make some conclusions about the size of this difference which we were after. And then we have this for large Z, like here, and for small z on the previous slide. And we can we then have to go backwards and do all our inequalities carefully. And it gives us the result in the end. So there's, I want to mention one open problem which I have found. So this last paper I wrote, this was from 2010. I've always found it very interesting. I've thought about it from time to time, but I haven't had any very good ideas of how to tackle it. Was the wrong direction. Okay. I used to work on integrable system with the Korteweg-de Vries equation, and there were some interesting functions which we used as potentials, and they were Weierstrass elliptic functions. This is P here. So these are meromorphic functions which have two periods in the complex plane. And if you, so omega is half of one such period, the complex one, let's say. Then it turns out if you take this potential here, it's a real analytic continuous function, and it's periodic. So we are in the plane, we have maybe one imaginary period, but we go along the parallel to the real line, and then the function is going to be periodic in that direction too. And this is Weierstrass elliptic function. It's a very famous function. It has all kinds of very important properties and plays a large role in evaluating elliptic integrals. Okay, so we have this function. And now the deal about this thing is the spectrum of the associated Schrödinger equation. If you use this as a potential in the Schrödinger equation, then you find something which has a gap. So there will be, the spectrum will consist of two intervals. One is a finite interval, and then there's a gap, and then there's an infinite interval. I mean, interval reaching out to infinity. So we are now not in the situation, as I mentioned earlier, where the spectrum is always one interval. Instead, we have a gap inside the spectrum, and then all our methods fall apart, which we have been using. All our methods have been relying on that the essential spectrum is one interval only. And this falls apart here, and one, in this case, one knows what one knows the solution. This is almost as good as the constant coefficients equation. One knows everything about the solutions in this situation. So this maps the energy lambda into the z-plane here. And one could now, so here in this case, one knows everything. There will be no eigenvalues and no resonances, and the spectrum are these two intervals, as I said. But now you could look at compactly supported perturbations of this situation, and that would not change the essential spectrum, but it would introduce eigenvalues and resonances. And one could then ask, will small such changes, what will it produce? Will it produce small small changes in the resonances? So what it would mean, since in the unperturbed case there are no resonances, it would mean if you perturb a little bit, then the resonances come in from infinity. And but this is something I found always very interesting, but I don't know exactly how to go about this to prove this. All right, this is all I have to say. Thank you very much for your attention.
Are there any questions? Yes?
So I mean, another way to define resonances is with dilation analyticity. So you have potentials that are dilation analytic, and but in the case that you have complex support potential, then they are not dilation analytic. But the super exponential potential, they can be dilation analytic.
I suppose if you do it that way, that you uncover, then the resonances appear as eigenvalues of your non-self-adjoint problem, and that would be the same resonances. But the important thing for us is that you can do it all the way, that you can cover. I think in the dilation analytic situation, you sort of go down a certain angle.
Yeah.
But what we need is we need to have this on the full complex plane, because our main tool is higher mass factorization theory, which is also the reason that in the one gap situation, the solutions are not going to be entire anymore. They are going to be these elliptic functions, and they are not entire. They are only they have very good properties still. But a Hadamard factorization theorem for this situation does not exist. And if you do the dilation analytic, you only uncover a piece of the plane, as far as I recall.
Yeah, that's right. But then for super exponential potential, decaying potentials, then you're going to do anything with the methods that you have?
One probably could, but it was already very technical in this way. I think one could, and in the case of the CMV operators, Maxim Zinchenko, my collaborator, has done something, but it's a much simpler situation because it's discrete.
Any other question? Well, I have a question. You mentioned the uniqueness when you know resonances and eigenvalues. Is there any characterization result in terms of resonances and eigenvalues?
No, I'm not aware of that.
Do you
actually, I have to take that back. I think Yevgeny Korotyaev has some results in this.
Has some results for, say, compactly supported potentials as well.
Yes. This is not a very interesting question in our case, because the the characterization would be something about the asymptotics. And my point of view is we don't care about the asymptotics. And the finitely many, they could be anywhere, that doesn't matter.
Okay, well, thank you. Then, oh, another question.
That is a good question. I know a little about this, or maybe nothing. But Tanya Christiansen in Missouri has an example of a potential, I think in 2D, where the potential is not zero and there are no eigenvalues and no resonances. This is very disturbing to me. So.
Yes.
Now, I understand that bound states, namely the zeros of the Yost function on the upper half complex plane, have some nice physical interpretation. Well, for example, you can trap atoms. On the other hand, the resonances, which correspond to the zeros of the Yost function in the lower half complex plane. So what kind of physical interpretations they have? Are there some instances, for example, where I can measure them, or I can see them, or I can observe them?
Yes, I think in my youth I used to be a physicist, so I'm not able to answer your question as well as I really should be. Anyway, I think you mentioned that eigenvalues have something to do with the absorption spectrum, and I think the resonances have something to do with the emission spectrum. And if you look at spectroscopy, you see the eigenvalues as very sharp lines, but the resonances, they are smeared out, and you measure the width of these. There's a distribution of intensity, and you measure the width, and the width has something to do in how much time the resonance will decay. So there are some real physical things in these resonances which you can observe. Therefore, you could, in principle, maybe you could look at some spectrum, and you see there are the eigenvalues, sharp lines, and there are the resonances, they are smeared out lines, and you see, of course, only finitely many. And then the idea is that, okay, this finite information still will give you something about what is behind that. Of course, our world is 3D. I was talking only 1D, so yeah, there's lots of things to do.
Yes, there's a question there.
I was wondering if you could use this type of analysis with the Drake equation for relativistic scattering processes.
I have not tried anything like this, but I think it could be done, yes.
Okay, thank you.
I see now, the Dirac equation is so similar to Schrödinger's equation in many aspects that I think it could be done, but I have not tried.
Any other question? Well, then many thanks for these enlightening lectures. And
thank you very much.